There's a bit of code on your phone that can hook into tens of thousands of methods all in the blink of an eye without you or your apps ever noticing. How does that work? Can we do better? And why am I on a trampoline? We'll answer all those questions, but first, what code am I even talking about here? This code sounds almost malicious, but it's the exact opposite. This is a developer tool written by Apple that you're probably already using if you're an iOS dev. It's called the main thread checker. It's very important on iOS that certain operations, especially anything that touches the UI, are called from thread 0, the main thread. Modern Swift code can help you force that at compile time, but there's a lot of old code out there, including most of Apple's own frameworks. So this tool just gives you a little warning if you call something from the wrong thread. Cool, that sounds almost trivial to implement, right? Like if I'm writing a method and I want to enforce that it's being called from the main thread, that's just a single line. Mission accomplished. We probably only want to run this for developers, so maybe something like is main thread checker enabled, and then we just check that. But I mean, yeah, it's pretty straightforward. We have our solution. But UIKit is huge, and Apple would need to add this check to tens of thousands of methods. There's no way they're just going to write this code everywhere. And it's not even just because of the sheer number. These UI methods are some of the most important bits of code on iOS. They are on the hot path for every app. Like even with a super efficient check, it is a pretty hard sell for Apple to alter the flow of all these methods across every single iPhone in the world. That brings us to the main design constraint that makes all of this so complicated. This check cannot affect production code. Not even a little, not even adding a single if statement. At Apple's scale, at the frequency these methods are called, it's just not worth it. In our own code, we might solve this by only compiling this check into certain builds. But this is Apple's code. Their frameworks are built into iOS. There's only one version of them we can use, and that's the production version. Instead, we're gonna have to do something more interesting. We can't change these production methods themselves, but we can change the way they're executed. What we want to do is essentially inject extra functionality before each method at runtime, conditionally, only for developers, only when this tool is enabled. And even this sounds like it shouldn't be too difficult, right? In some languages, this would be hard, but most of Apple's frameworks are implemented in Objective-C, which makes changes like this surprisingly easy. Even if you're not an iOS dev, you've possibly seen it on this channel before. We call it method swizzling. But we're gonna get a bit weird with it in this video. See, our normal setup works like this. If I start with a basic Objective-C class, with this method that just prints out hello. If I run this program, hello is printed out. But swizzling lets us change what happens whenever someone calls this say hello method. We'll start by creating a new Objective-C file, and in this file, we'll add a new method to our messages class. I'll call it main thread check, and within this function, we'll check if we're on the main thread or not. Now, nobody's calling this method, so if I rerun the app, we still just see hello printed out. But swizzling lets us change that. First, I'm gonna import the Objective-C runtime header. I'm gonna make a load method to run automatically when this binary is loaded. Then I'm gonna reference our original say hello method by using class get instance method. Next, I'm gonna do the same thing to get a reference to our replacement method. And then I'm gonna use the runtime function method exchange implementations to tell the runtime to swap those two methods around. Meaning whenever somebody calls one, it should call the other, and vice versa. Now, if I rerun, even though our code is still just referencing this say hello method, because we've told the runtime to swap that method out with our main thread check method, we see this main thread checker line printed out. Of course, we're no longer actually getting to that say hello method at all now. But remember, because we swapped these two implementations around, anyone who calls say hello actually gets to main thread check, sure. But the inverse is also true, which means that if we write code that calls main thread check here, even though it looks like this should just recurse indefinitely, if I rerun, we will see that we actually end up getting to our original say hello function. So this is pretty neat. If we go back to our main file and I move this call to a background thread, then if we rerun, we'll see that our main thread check actually does work. And we did this without ever changing this original implementation. We could easily add a check when we set up the swizzle to only run it if some developer setting is enabled. And if that setting isn't enabled, then our check doesn't run. Perfect. And this might not be a surprising setup to you if you're used to swizzling already. But here's the big question. How do we handle two methods? Or 3 or 4. That sounds easy. Obviously, I could make another copy of this method, make another copy of this setup, and do exactly the same thing again. But remember, we're talking tens of thousands of methods here, and that's not gonna scale super well. What we really want is a single method that everything can go through. Now, it's actually not too hard to make both of these methods route to the same place. We can add a new method that's responsible for swizzling whatever method is passed to it. It's gonna be just based off the class and method name that were passed into this function. And then we're gonna get our replacement method, and that's always gonna be this main thread check method down below. Let's actually move that out of the messages class to make things easier. So we get whatever method is passed in, we get our main thread check method down below. But this time, instead of swapping the implementations around like we did before, which doesn't make much sense if we're trying to get multiple methods to just point to the same place, we'll instead use method set implementation to just say anytime somebody calls that original method, route them to wherever this replacement method lives instead. And now this recursive style call down here won't work. We'll get back to that in a second. Now say we're calling both of our example methods. We have messages.sayhello and messages.saygoodbye. And we wanted to add the main thread check to both of them. all we have to do is swizzle those two methods by calling our new functionality that we just added below. And if we re-enable our main thread checker and rerun this, we can see that this main thread check method is called twice. Great. Both methods are now pointing to the right place. We could see how we could scale this up to like tens of thousands of methods all running the same shared check. But of course, now we need to get back to the original method here. What exactly do we write to do that? Before, when we were swapping implementations around, we knew we could just call main thread check to end up at say hello. But now this is tricky. We want to take multiple function calls, route them all to the same place, but then have enough information pulled from somewhere to know how to route them back. Now, Objective-C does something really cool that actually could help us here. Objective-C methods might look weird, but they're really just C-style functions under the hood. So this sayHello method is implemented in the binary as a function that looks something like this. Every Objective-C method starts with two implicit parameters. Self, that's the object that this method is being called on, and _cmd, which is the name of the method being called. When you call a method like messages sayHello, this translates under the hood to a C-style function call that passes in the object and the method being called. And Obj message send uses this information to look up where the implementation of this method lies, and then call that implementation. That's why swizzling is so easy in Objective-C. You're basically updating the data structure that this is using to look up where methods live. But point being, these two implicit parameters are necessary for Obj message send to route messages correctly. And these parameters are available to us in our Objective-C implementations, and both of them could be super helpful. For example, we could update our log statement to print out the information in both those parameters, like what our class is and the name of the method being called. And with that update, we can see that we actually know what method we are trying to call, which should be enough info to then route back to the correct place accordingly. So you could imagine code like this, where we convert the method name to a string and then call the correct function based on that name. But we still need a way to actually call this function. Right now, we're basically just overwriting it up here. There's no pointer back to this original implementation, but we can save one. Before replacing the implementation, we'll get the current implementation using method getImplementation. And then we actually need to store that somewhere. So I'm gonna make a dictionary to hold them. And now every time we rewrite an implementation, we can make a key based on our class and method name, and then save the implementation under that key. So now we should be able to properly route to these. In our main thread check method, once the check is actually done, we'll construct the same key and then look the implementation up in the dictionary. We should have a pointer to our actual original function here. But now we need to actually call it. So I'm gonna make a new typedef for a function pointer that returns no value but takes in these two types. Because remember, all Objective-C methods start with those two parameters. And then we can cast our implementation pointer to that type. And then finally, we can call the actual function using the same self and CMD values that we're already logging further up in this method. Remember, that's the instance this method was being called on and the name of the method that they were trying to call. Now, if we rerun, we should see we get a main thread check for that sayHello method, and then we call that actual sayHello method successfully. We get a main thread check for say goodbye, and we call the goodbye method. Great, we've got a basic main thread checker working. We've added some logic to multiple methods all in one shared handler without ever touching the methods themselves. Now, we're still hard coding some information about these methods up here, but we don't have to be. We could instead look up those methods at runtime. We could use class copy method list to get a list of all methods in a given class. And then for each of those methods, we can say, go ahead and swizzle it. And we'll update this signature down here to match. And now instead of hard coding these two methods, I'm just gonna say swizzle everything in the messages class. And with that, our swizzle still works the exact same as before without us writing a single line of code that's specific to the methods we're hooking into. So this is where we start to see how we might have a single shared handler that does something like a main thread check enabled entirely at runtime, exactly what we needed. But there are two big issues with the setup. For one, what happens if a method takes in a parameter? Remember, this is going to compile to a C-style function that takes in three parameters, self, _cmd, and now this name parameter. If we try calling this method now, we'll crash. Something about a bad memory access. Because over in our main thread checker where we get a pointer to the function we're trying to call, somebody needs to know to pass that name parameter here. But how do we do that when every method has different parameters it needs, different types, different counts? And where do we even get their values in the first place? Like, how do we get access to name from here? Funnily enough, Objective-C also has something that could help with this. It's called NSInvocation, which kind of packages up parameter info for weird forwarding cases like this. But A, it is super slow, like 100 times slower than the normal method call. There's no way we could route all UI calls through it, not even for a dev tool. And B, even this wouldn't save us because we have an even bigger issue here. You might have thought of it already based on the way we're looking up what method to call. What happens if we hook into a subclass? Let's say we make a new subclass of messages called messages v2. And in this subclass, I override sayHello to log a new message and then call super super say hello. Now let's set up our code to call this new method. And now let's make sure we're swizzling messages and messages v2. That way, if anybody uses either of them directly, they get the main thread check. But what actually happens when we swizzle both? Think about it. What's going to happen when we call this say hello method? We can step through with a debugger and see. Now remember, we've swizzled this method, so anytime anybody calls this, they should end up in our main thread checker instead. The main thread checker is going to say that it sees somebody calling a method named say hello on an instance of a class called messages v2, just like we'd expect. It's going to do its main thread check. It's going to look up the original implementation of say hello, and then it's going to call that function. And perfect, we've ended up in messages v2 say hello. And now we're about to call super say hello to call our parents implementation. But what's going to happen now? Well, that's a method on messages, and we've swizzled everything in messages. So we're going to end up in our main thread checker again. And it sees once again that we are calling a method named say hello on an instance of a class of type messages v2. This is a problem. From the perspective of the main thread checker, remember, we're calling say hello on our superclass right now. The method has the same name and we're calling it on the same object. So when we look up what method we want to forward to, we end up back in our subclass's overridden method. If I hit resume here, we're stuck in an infinite loop. All we see is a reminder to subscribe over and over again, unending and unyielding from now until the end. Oh, we crashed. That works too. So we finally hit the big problem with using this shared handler here. We can easily point as many methods to this handler as we want, but we just don't have enough data to know consistently where to actually route back to. It's not enough to just know the type of the object we have and the name of the method being called. We've seen how overridden methods break that. We need to know specifically where we were going before the swizzle. But even if you factor every possible bit of information available to you in an Objective-C method, there's just not enough information to figure that out. So how does Apple do it? I actually wrote an article years ago on Brace.co about reverse engineering Apple's implementation, but a few things have changed since then, including having an entirely different CPU architecture. And that matters because we are going to have to get down to the assembly level here. There's a couple ways to figure out where this logic is implemented, but as always, one of the easiest is to find some relevant output text and then work backwards from there. If I try to touch something related to the UI on a background thread, like just initializing a view and printing it out, when I run, we see an error triggered in Xcode from the main thread checker. And we see this console output, main thread checker, UI API called on a background thread. This feels like a pretty distinctive string, so I'm going to copy it. And then over in terminal, I'm going to cd into my Xcode application folder. And then I'm just going to grep for that string. And we can see a couple matches start to appear for things like testing and automation, but by far the most interesting sounding result is lib main thread checker. This is interesting. It's its own dynamic library, which means if we pause Xcode right now, main thread checker is enabled. We just saw it. And in the debugger, I call image list. We should be able to see every library that's currently loaded. And if we filter down, lib main thread checker is here. Cool. And if we disable the main thread checker by turning it off in this diagnostics window, and if we go ahead and rerun, of course we don't see that error printed out. But if I pause and do image list again, we can also see the library is not loaded at all. So that's definitely our culprit, and helps highlight that this is a change that runs entirely at runtime, just based on whether or not this one library is loaded. Super cool. Let's open this in a disassembler and see if we can figure out how it works. I'm using IDA today. A couple people have asked if you really need IDA. Absolutely not. Use whatever you have. It's just the one I am used to. So I'm going to find lib main thread checker here, and I'm going to go ahead and drag it in. There are multiple executable types in here, but my phone is ARM64, so that's what I'm going to use. So the first thing we see at the very beginning of the binary is a function called handler start, followed by something called trampolines, followed by tens of thousands of tiny functions, each of which only contains 2 instructions. Okay, some things from the intro are starting to make sense now. These are super interesting, but let's keep looking at what's down here and then come back. Really just tens of thousands of these. There we go. Here we can see the other functions implemented in this library. There's not that many, but library initializer feels like a great place to start. I'm going to decompile this method so we can get a quick rough look at what's happening. It looks like we're reading a bunch of settings from the environment. The last one is a suppression file, and then we've got, it looks like, a lot of handling related to those suppressions, which could be interesting, but let's keep going for now. I'm just going past all the suppression related stuff. And then down here, we're looking up some specific classes in specific frameworks. AppKit is the UI framework for Macs. UIKit Core is the UI framework for iOS, which makes sense. Down here we can see they're looking for the WebKit framework as well. And we're just, assigning, setting up a bunch of things, but it looks like down here we have a call to something called initialize trampolines. And that takes in a function as a parameter and saves it to something called registered callback. And then we set first trampoline equal to, this very first tiny function that was up here. Okay, and again, this register callback is just based on whatever function was passed to this initialized trampoline. So let's go back and look at what that was. We're passing this checker C function, and this looks like where the actual main thread check happens. We check if we're on the main thread. If we're not, then we call some other function, which does a bunch of things, but ultimately calls assert API must be called from main thread failed. And I bet in that we can find the actual, yeah, there it is, main thread checker UI API called on a background. That was the actual error message we saw in Xcode. Great, so we know where our actual main thread check lives. That's all in this initialized trampoline setup. What happens next? We grow the capacity of some data structure, and then we call swizzle classes. And it looks like this method looks up every class in the given framework. It logs swizzling class, and then it gets all of the methods in the class, very similar to what we were already doing in Xcode. We maybe skip a few dangerous methods that we don't want to swizzle. Retain and release and auto release are all related to memory management. Is equal, you can, it actually says up here, that's safe to call across different threads, so that makes sense too. So here we're choosing what things we actually want to swizzle. And then there's a bunch more explicit ones that it seems to be skipping down here. And if we've made it all the way down here, we call something called prepare swizzler. And prepare swizzler, we pass in the class, and then v21, this must be the method we're swizzling. And then what does that actually do? It gets the implementation of that method. That's going to be a pointer to where the method actually lives in memory. And then we call add trampoline, passing in that implementation we just found and our class name and our method. So this makes sense. This was structured very similarly to what we were already doing in Xcode. Like find the classes we're interested in, iterate over all those methods, get the implementation of those methods. It's very similar. So where do we start to differ? If we click into add trampoline here, we have some variable that is the number of trampolines used. Then we have some sort of data array where we save all the information we passed in. You save this first parameter was again the implementation where the function was defined, and then the, I think, method name, and then the class name, and then some empty space at the end. And then we return a trampoline. This +8 here is the size of one of those small functions we were looking at earlier. Each of these functions is 2 instructions long, and in ARM, a single instruction takes 4 bytes. So a total of 8 bytes for this whole function. So the first time this code runs, trampolines used is going to be 0, so we're adding 0 down here. We're going to return a pointer to the first trampoline. Then the next time it runs, it's going to add 8 bytes, which is going to return the second trampoline, then the third, then so on and so forth. So great, we see a pretty similar structure to what we had before, but this time, instead of using a shared handler, every swizzle is getting its own little mini function. But what even are these functions doing? What is a trampoline in this context? Well, generally, a trampoline is just a small bit of assembly whose job is to do maybe a little bit of computation, but mostly bounce you over to some other part of the codebase. Trampoline bounce, you get it. They're used in a few different contexts, usually created by the compiler itself. Like if we scrolled further down in this binary, on iOS, anytime you call a function that lives in a different framework, we end up in a small trampoline, in this case a kind called a thunk, whose job is to read where the real function is and then bounce you over to it. This is a branch instruction that means go to whatever's in this register. They're usually just an implementation detail behind the scenes. Our code doesn't know or care that we're going through some intermediate function here. This code doesn't touch the stack, so it doesn't even end up in the stack trace. Its only job is to just bounce us over to the real implementation. So with that in mind, it makes sense that these little functions are called trampolines in this code base. They're doing a bit of work and then bouncing us over to some other function. What is this bit of work they're doing? Well, ADR gets the address of the current instruction, plus an optional offset. But we have no offset here, so we're just getting our current address with this instruction. And then we're putting that value into register x16. And then we're branching over to something called handler start, which is presumably going to do something useful with that value. Let's actually follow along in our own project here. It's actually pretty easy to add our own assembly like this. I'm just going to create a new assembly file called trampolines.s. We're going to say these instructions should live in the text segment, which is where code lives in an executable binary. And they should start at an offset divisible by 4, which is an ARM requirement. Each instruction is 4 bytes long, so it helps to keep them aligned to that number. Just a standard setup so far. Now I'm going to make a label called trampoline start, and let's mark it as externally visible outside of this trampolines file. And now let's make our trampolines. We're going to, again, just completely follow along in what we're seeing in the disassembler. I'm going to use an ADR instruction and move something in x16. And we can use a period to say, use whatever the current instruction address is. So when this actually assembles, it will turn into something equivalent to this. And then we're going to branch again to some shared trampoline handler. And we basically just want a bunch of these. Those are our trampolines. That matches what we're seeing in this file. We could copy paste them like this, but we can also use the repeat directive to give us a fixed number. Let's say 100 for now. That will be a lot more efficient given how many of these we seem to need. And now we can define this shared handler further up in the same file. But what's that handler actually doing? Well, there's some interesting stuff in here. Our disassembler is trying to assign variable names to everything, but I think it's clearer without them, so I'm gonna shut them off. So it's fairly common to see a disassembled function start out with assembly like this. This is kind of a standard function setup. We don't need to analyze it too closely here. But if you're curious, we're storing 2 registers onto the stack, and these registers have special values. x29 stores our caller's frame pointer, the base of their stack frame. Basically the address at which they can start to store any temporary data on the stack. And x30 stores the address that a function should return to when its work is done and you hit a return instruction. Again, don't stress this too much if this is new territory to you. Basically, they're both metadata owned by whatever function called us, and by the time our function is done executing, we should actually be able to see down here, we want them restored back to their original values. So it's normal to see these backed up at the start of a function and then restored at the very end. The second command here is very similar. We're updating that same frame pointer, kind of setting the stack space up for our own function. Very normal. Things get a bit weird after that though. We're storing a bunch more registers, starting with x0 and x1, all the way up to x8. And then we store q0 through q7 as well. So we're just storing a bunch of registers on the stack. If you know a bit about assembly, something big might have just clicked for you with how this implementation works. But we'll come back to it in a sec. For now, just know that we are storing a bunch of register values. Now what's happening down here? Well, it looks like we're setting up for a function call. So an important thing to know here, for C-based languages, when you call a function, the parameters to that function are passed in registers, starting in x0 and counting up. Like if you're calling a function called add and passing in the values 2 and 3. That's going to translate to assembly where we set the value of x0 to 2, set the value of x1 to 3, and then we call our function. We also use registers to return values back from a function. So in this case, if we wanted to read the return value from this function after it runs, we can find it in x0. The rules get complicated in more advanced languages and with things like structs and floating point numbers, but this is kind of the base case. So with that in mind, we can parse through what's happening here. We know we're going to be calling a function called trampoline C, and up here we're setting up the parameters to that function. Now I'm guessing by that function name that it's implemented in C, but I'm gonna code alongside in Swift. We'll make a function that we can call from assembly in a new Swift file. I'll call it trampoline handler, and we can make it callable from assembly using this Silgen name annotation, short for Swift Intermediate Language. The leading underscore makes it clear that this is not a stable API yet. But like, what am I gonna do, write this in C? So we know this is a function, but we don't yet know what parameters it takes in or what information it returns. But we should be able to figure that out. It looks like the first parameter is gonna be whatever's currently in x16. We haven't touched that register anywhere further up in this function. So remember, from our trampolines, each trampoline set its own address into register x16. So the first parameter to this function is gonna be the address of whatever trampoline we were coming from. The second value is a little harder to parse. Remember, x29 is our frame pointer, the base of our stack. The stack grows downwards, so usually we're reading values below that frame pointer. But in this case, we're reading the value 8 bytes above our own frame. That ends up being the last value that was saved to the stack before we updated the frame pointer here. In our case, we can see that last value. It's right here, it's x30. And remember, x30 is our link register. Again, basically the address that this function is supposed to return to. Whenever you have a branch with link instruction, like the one we're using down here, x30 is automatically set to the address of whatever the next instruction is. Then when this function returns, execution will continue at whatever address is currently in that x30 register, meaning this function returns and execution continues right below it. So from this, we can get that trampoline C takes in 2 parameters, the address of the trampoline we went through, and the address that whoever called us wants us to return to, which I'll call trampoline return address. So what does this trampoline C function actually do with that data? So a similarly normal function prologue at the top, we are saving some registers that we are then going to restore at the end of this function. And then we set up our stack for the rest of the function, again, normal. Next, we are getting the address of the first trampoline. This takes 2 instructions in ARM, one to get the memory page where that address lives, and then one to load the symbol within that page. Point being, at the end of this, x8 contains the address of our first trampoline. The equivalent in Swift would be something like this, where we get a handle to any currently loaded image, and then using that handle, we look up the address of trampoline start. That gives us a pointer object, and then we'll have to convert that to a plain old integer value. Cool, back to our assembly. Remember, x0, our first parameter, is the address of the trampoline we're coming from. We're gonna take that address, subtract the address of the first trampoline that we got from the instruction above, and then save that back into x8. So we're effectively getting the offset of the trampoline we went through. If we imagine getting here through the first trampoline, then its address minus itself is gonna give an offset of 0. If we came through the second trampoline, its address is 8 bytes higher, so we're gonna get an offset of 8, then 16, then so on. Now we get to some silly looking math. We add 7, we compare our offset with 0. This looks weird, but it makes more sense when we get to this LSR instruction. This is the logical shift right. In binary, shifting a number to the right is the equivalent of dividing it by 2. Just like how in decimal, shifting a number to the right is equivalent to dividing it by 10. So we're dividing our number in half 3 times, which is equivalent to dividing it by 8. Everything happening above, like adding 7 here, is a compiler trick to get the right rounding behavior if x8, our trampoline offset, happens to be negative. We shouldn't have to worry about negative numbers here. I'll leave it up to you to figure out why these instructions work for that case if you want. But end result, in our expected positive case, this is just dividing our number by 8. Remember, the first trampoline is going to have an offset of 0, then 8, then 16, and so on. So by dividing by 8, the number of bytes in each trampoline, we get the index of the trampoline we went through, 0, 1, 2, so on. Now it looks like we're going to load something from this data array. We saw this array before, down in add trampoline. This is where we stored information about a function just before swizzling it. Specifically, we're saving each of the pointers that was passed to this function. I believe that was the original method's implementation, and then the name of the method, and then the class. And then again, we're leaving the 4th slot empty. So if we go back to the function we were just looking at, we can see we're gonna take our trampoline index that's currently in x8, we're gonna shift it left 5 times, that's the equivalent of multiplying by 32, which makes sense given that's how many bytes of data we're storing per trampoline. And we're gonna take that value and look up those bytes in that data array. So this is just basic array access. It looks complex on the assembly side, but our Swift implementation can be pretty straightforward here. I'm gonna make a new struct to hold on to our trampoline data. I'm gonna store the exact same things that Apple's storing in their implementation. The original method implementation, its name or selector, and its class. And we need some collection to actually hold that data where we can look it up based on index. So I'm just gonna create a giant shared array where for trampoline number 0, we will store its data at index 0. And now in our trampoline handler, we can look up that trampoline data, and that will have access to all that useful data about the trampoline. Great, so back in assembly, we're getting that data, we're putting a pointer to it in x19. We're gonna load the address of our registered callback. Remember, that was the thing that's actually checking if we're on the main thread or not. We're gonna take that pointer of our trampoline data and copy it from x19 into x0. And then we're calling, this is a branch with link to whatever's in this register instruction. We are calling that registered callback to check if we're on the main thread. And based on what we learned earlier, we can infer that this trampoline data that we moved to x0, that's the first parameter to this registered callback function. So that makes sense. The check gets full context of what method was being called. All that data that was stored when the trampoline was first registered. So it can do things like print out the class and method where an exception occurred, or maybe exclude certain classes, whatever it wants. There's actually one more bit of context passed to this callback, even though we can't see it right now. Remember, when we called this trampoline C function, we also set this register x1 to effectively the address of whoever was calling the trampoline in the first place. We do not touch that register anywhere in this function, which means there's actually a second parameter passed to this function. It was just set up by the previous function. We can actually check how that parameter was used. Remember, this registered callback was set all the way back in this library initializer, where it was set by initialized trampolines based on whatever function was passed here. And so we can see our disassembler thinks this function takes 2 parameters. It's called them A1, which we know will be our trampoline data, and A2, which was this trampoline return address. If this check calls, if we aren't on the main thread, then it passes both of these to that error function we were looking at earlier. It actually flips the order around here. And if we look at how that parameter is used, we can see that we're looking up the binary image that contains that address. And down here, we're seeing if that image's path starts with system, or put a different way, was whoever called this trampoline coming from an Apple system framework. This makes sense. This explains why we care about this data being passed around. If we've gotten this far, somebody has called a method on the wrong thread. We have failed our check. This check is a way to say, don't throw an error if that bad call came from Apple's own code. That's a very good design. That's important for 2 reasons. One, if Apple did mess up and is calling something from a thread they shouldn't be, there's not much we can do as developers there. We don't want to see errors for that. They're completely unactionable for us. But 2, more importantly, methods call other methods. If I call something like UIView.addSubView on a background thread, that's going to call dozens of other UIKit methods, and those methods are going to call dozens of other methods. If we write one bad line of code that's calling something on a background thread, we don't want thousands of errors. We want one error in the place where we are crossing from our own code into Apple's code on the wrong thread. So this lets us ignore all those internal calls, since the checker will see that they are coming from within Apple's frameworks. That's awesome. So now we know we are going to want a shared callback that passes along our trampoline data and the address of whoever called our trampoline. And then I'm going to wrap all this in a class just to make it more accessible. Cool. And then we can call that shared callback right down here. And this is a nice design. This way, somewhere else in the app can be responsible for deciding exactly what the check should do and how it should behave. In our case, we'll finally write the code to actually check if we are on the main thread or not. And we can even log all the information about our caller because we have access to it here. Okay, so we understand the check now, how context is passed to it, and what it does with that context. But that was never the hard part. Now that we've done the check, how do we get back to the original method we were trying to call? Let's keep following our assembly after the checker is called. So we've just called that registered callback here. Remember, x19 contains our trampoline data. This load instruction is going to load whatever the first value in that data is. We found earlier that the first value here is going to be a pointer to the method's original implementation before we swizzled it away. So after this load command, x0 now points to that original function implementation. Now we do our normal function prologue, restoring those registers we saved at the beginning, and we return to whoever called us. In this case, that other other handler that we were looking at before. Remember, x0 is the register that a function will normally use to return a value. And in our case, we know that x0 was set to the address of the original function implementation. So then here we're going to add at the very end of our method, return our trampoline data destination, the original implementation of the method we're replacing. So we've returned that here and we are now storing it into x16. And we can see that at the very end of this function, we end up branching to whatever is in that register. We can now see how Apple fixes one of our big issues, getting our code back to the right place. We found earlier when we built our own shared handler that there was not enough context passed to figure out where to route back to. These trampolines are effectively a way to add more context. When we swizzle a function, that function gets its own trampoline and its own entry in this huge shared data array. Each trampoline passes its address to this shared handler. The handler uses that to figure out the trampoline's index, look up its stored data, which includes a pointer to the original function implementation. And when all is said and done in this handler, we branch to that original implementation. We're not looking that up based on method names, so there's no chance of collision like there was before. We look it up based on trampoline index, and every single thing we swizzle gets its own trampoline. So what's with these registers? Well, remember, when we call a function in C-based languages like Objective-C, we've already seen how parameters are passed into those functions, starting in x0, then x1, all the way up to x8. These Q registers are the same thing, just for floating point values. If you called an add method and passed in 2.5 and 3.5, those are going to be set in Q0 and Q1. We are storing the value of all of those registers onto the stack here, and just below, we're restoring them. We're making a temporary backup of any register that might contain a parameter, calling our checker, which is going to call a bunch of other things and overwrite registers and do whatever it wants. It does not matter, because once it's done, we are going to restore all those original register values that we stored up above. That's how Apple solves our other big problem, forwarding parameters back to the original function. It never cares how many parameters there are or even what's in them. Some of these probably contain parameters, some of these probably contain garbage data from previous calls. It does not matter. By the time we get to these final instructions, where we do our normal function epilogue and then jump back to the original implementation, by the time we get here, everything at an assembly level has been restored to its original state, without us ever needing to have cared about what that state is. The registers that store parameters, the stack, our link register, exactly as they were before, exactly in the state they would have been if we had never swizzled anything at all. So that when you branch to this original method, it is none the wiser. And since we've been coding alongside, we actually only need a bit of code to hook this up. Let's get rid of our old swizzling implementation and set up a new one that can use these trampolines. Just like before, I'm going to get the original implementation of a method, but now we need to replace it with one of our trampolines. To do that, I'm going to make a new variable that is just a raw pointer to whatever our next trampoline is, starting with the very first one. It's going to use a very similar setup to what we've already seen, where we look up the trampoline starts label at runtime. And now we can take that trampoline and use it as the implementation for whatever the method we're swizzling is. Then I'm going to store this trampoline's data in that giant shared array, which includes where the original implementation lives, and its name, and its class. And finally, we'll set up the next trampoline by moving this pointer 8 bytes forward, the size of each trampoline. So each time this code is called, we are replacing this method with whatever the next available trampoline is and storing all the method's original data. And just like before, let's add a quick method to swizzle everything in a class, which just uses the method we already made below. And then we'll add one more method to actually kick everything off, swizzling the same messages demo classes that we had before. Remember, with our old implementation, this would break as soon as messages v2 tried to call a superclass method that it was overriding. We couldn't tell where to route to. But this time, if we call that same method and rerun, we can finally see, even with our subclassing, this design can indeed hook into whatever methods it wants fully generally. This superclass call still works. And nothing about this setup is specific to these demo classes. This can swizzle everything. We can test that easily if I drag all this setup into an iOS project. And this time, instead of swizzling just these two classes, I'm gonna look up whatever binary image contains UI view, kind of similar to what we saw in the disassembler before. And then for every class in that image, we will get the class's name, and we'll call our swizzle function on that class. And this time we look up every class in UIKit and swizzle every single one. That's all we need to make this a full UIKit main thread checker. Now, of course, we need one trampoline per method we're swizzling. So I'm gonna go to our trampolines file and say we need 113,018 trampolines, the exact correct number required for UIKit on the version of iOS my phone is running. And now if we rerun, we have a working main thread checker. You can see all of the methods it's swizzled that's printing out. It even caught an issue because somebody within Apple is calling some rotation animation controller method on a background thread. We already learned how we could filter out internal calls like that. We would do that right here by looking at caller address. But incredible, we can see that after all this insane setup, it is indeed working. And my favorite part of all this, there's no special API that Apple is using here that only they have access to. This is all just clever ideas and good custom assembly code that you can implement yourself. In fact, I know at least a few companies have built their own version of this based on my original post a few years ago, so they could catch these kinds of errors and integrate them with their own error reporting. It's a really nice design and is almost a perfect implementation. But there is still that almost. And maybe you got the same hesitation just a minute ago. Because if you were looking to ship your own version of this, there is a big question that we just skipped over there. How many trampolines do you need? Like you personally. I mean, this is easy if you're Apple. They know they're gonna be swizzling everything in the current version of UIKit. They can count how many methods are in there and just make sure to include more trampolines than that. This is a pretty optimal design as far as Apple is concerned. Everything works great. But this is a harder problem for you. Imagine you wanted to make an open source version of this and ship it for distribution. You want this to work with the current version of UIKit, but you also want it to work with all future versions of UIKit. You don't want old versions of this framework to crash people's apps just because they updated their phone. And people who want their own custom callbacks that have nothing to do with the main thread, and just want the ability to inject code into hundreds of thousands of methods for a use case that you or I could never dream of. How many trampolines do you include for them? There are some easy answers here, like 1 million. But at 8 bytes each, that's a solid 8 megabytes of trampolines. A pretty significant app size hit for code that will be mostly unused in some circumstances and still not be enough for others. You could also leave it up to developers, make it a configurable build time setting. Works fine, but definitely makes the library a lot less magical. There would now be a whole big piece of documentation you'd have to read in order to figure out how to derive this magic number for your project. It'd be fine, but the best possible implementation of this is clearly one where you never have to choose this number in advance at all. We'd instead have a library with a super small footprint that could grow to handle any use case we could never even imagine. But if you know iOS well, you know that's not really possible, right? We know we need a unique trampoline per method we're hooking. That's how we identify where we came from and where we need to go, so there's no way around that. Meaning if we want to swizzle an arbitrarily large number of methods, we need a way to create an arbitrarily large number of trampolines. And that's a problem, because now we're talking about creating new code at runtime, and iOS does not like when you do that. This is a thing we can totally do on the Mac. If we take a new project and opt out of some of the default memory protections, then you get a surprising amount of flexibility. It's possible to create essentially brand new functions at runtime. First, you'd want to use something like mmap to create a new page of memory. Mmap is more commonly used to map files into memory, but it's also a convenient way to get just a chunk of memory where we control things like memory protection settings. We'll say that we don't care where this memory is placed and we'll request a single page of data, which is the minimum. And now we say what protections we want on this memory, like if we want it to be readable or writable or executable. Now, even macOS doesn't allow memory to be writable and executable at the same time. You could imagine maybe some security downsides that would come from allowing that. So we can't use all three of these at once, but we can do something fun here. Let's start by just marking the memory as readable and writable. Now to finish up this call, I'm gonna say this memory is just for our process, that's mmap private. And then again, this is usually used to map files into memory, but we'll say we have no file, that's map anonymous, and no file descriptor or file offset, just give us memory. Now we have a new page of writable memory and we wanna write some instructions to it. So I'm gonna create a new array to hold the bytes of those instructions. And let's figure out what we actually want to put here. Say we wanted to create an assembly function that just returns the number 7. Now we need to know the actual bytes that correspond to those instructions. So I'm going to bring up armconverter.com. It's a nice easy way to get that. And I'm going to add our instructions there. And so here are the literal bytes that these instructions would assemble down to if we assemble them into a binary and then open that binary in a hex editor. So I'm going to take these instructions and copy them back to our code. Now we need to actually write those bytes into memory. So I'm going to get a pointer to that data and copy it into the function memory that we just allocated. Swift makes this a little weird, but we're just copying these bytes into the memory we created above. And now we can tell Swift, treat that pointer as if it were a function. You know you're having a fun time when Swift keeps being like, are you really sure you want to do this? Anyways, we'll say it's a C-style function that takes no arguments and returns an integer. Now we have a function we can call. But if we try running this now, we're gonna get a crash, and that's because our memory is not marked as executable. So there's one more thing we have to do here, which is change the protections of this memory. So after we've written our data, I'm going to call the function mprotect, and I'm going to pass in our page of memory. I'm going to say it's a single page long, and I'm going to say we now want it to be readable and executable. This is kind of fun, right? macOS doesn't allow us to have all three at the same time, but we can say the memory is writable, write to it, and then update it to say it's now not writable but executable. And now when we rerun, we should see we've created a crash. What did I do wrong? Let's debug. So if I print out the bytes in function memory, we're expecting to see all the bytes we wrote up above. Oh, and they're there. There's E0, there's 80, there's D2, but they're really spaced out because Swift thinks this is a bunch of 64-bit integers, but really we want just bytes. Okay, now if we try rerunning, cool, we can see we've created a function purely at runtime that just returns the number 7, right? We took the assembly instructions for that, we wrote them into memory, and then we were able to invoke those bytes and get something out. Cool, now all that is to say, this would be an ideal way to create more trampolines at runtime. Whenever we need more trampolines, we could just allocate a page of memory, write our trampolines there, and call it a day. But we want this to work on iOS, and iOS always has more strict memory protections. If I copy this into an iOS project, it won't run. There were some tricks to get things like this working in the past, but they have all been patched for years. You can't write code like this without a special just-in-time compilation entitlement from Apple that the vast majority of apps don't have access to. Okay, so we need one trampoline per function, and we can't create new trampolines from scratch at runtime. That means we're stuck, right? We just need to put a million trampolines in the binary and hope that nobody has more methods than that? Well, not quite. It turns out there's another path we can take here, and it's weird. I first learned about this kind of strategy from Landon Fuller's blog, where he wrote an article 15 years ago. God, I think I remember reading this when it came out. Am I getting old? Anyways, it was about a new Objective-C feature that Apple had added in iOS 4. Apple had a surprisingly similar use case involving trampolines to move around argument registers, and they solved it a different way. The trick back then was that even though you couldn't create new code at runtime, you could remap existing code. Our modern operating systems use virtual memory. The memory we see from within our program does not directly correspond to where things actually live in RAM. Instead, our program is given a nice, clean, huge address space, and under the hood, the kernel will map those memory pages to actual physical areas of RAM, or to higher level things like files on disk or memory shared with other applications. That setup helps power a bunch of things we take for granted, but the important point is, when our app has a page of memory that lives at, say, hex 1000, we really mean there's a virtual mapping pointing from hex 1000 to somewhere in physical RAM. And we have some control over this mapping system, which means we can ask the system to create a new mapping at a different address that points to the same underlying memory. These look like two completely different blocks of memory from the perspective of your process, at two entirely different addresses, but they're really just two views of the same underlying RAM. And there's some really cool use cases for that. One of my favorites is covered in an article from Mike Ash, where he talks about a ring buffer, a kind of circular data structure that can be very efficient, but can be annoying to read from. You can't just hand a consumer a pointer and say, read X bytes of data from here. Instead, you need logic to do bounds checking and loop back to the front and everything. With virtual memory, we can set up the following page of memory to point to the same underlying area of RAM. Again, just two different views of the same underlying data. And now it's possible to return a pointer that points to all of our elements continuously in the correct order. So there are real applications of memory remapping, but it's pretty rare that you'd want to use this for executable code. There's a huge issue here, which is that your code will probably no longer work the way you expect. But let's look at why. Back in our original project, I'm going to temporarily replace all of this assembly with a single function to help make our testing easier. Its job is to return the square root of 7. So I'm going to load the value 7 into a register, and I'm going to call the square root function. Now, if I set a breakpoint on this print statement and run our code, we can step through what's actually happening during this function call. I'm going to use SI to step forward at an instruction level. And we can see that we first enter our assembly function. We're about to load the value 7 into that register, and then we're about to call the square root function. If I keep stepping, we'll end up in a little trampoline, the same kind we saw earlier, that gets the address of the real square root function because it lives in a different library. And then we branch to that real square root function, which is going to do its calculations and then return. And now if I just continue execution, we can see our square root value printed out. So that's how everything should work, but let's try this remapping trick we just learned about. There's two things we need to do here. The first, to keep the math easy, I'm going to update our assembly to say that our function should be aligned to a page boundary. We're saying make sure whatever comes below this starts at an address that is a multiple of hex 4000, which is the size of a single page of memory on iOS. Remember, remapping deals with memory pages. We can only remap entire pages of memory, so it'll make the math a lot easier if we can know that our function is at the start of a page. And now the real star of the show here is a function called VM_remap, which takes a lot of parameters because it can handle a lot of different use cases. But they're actually pretty straightforward for our use case. We're creating a new memory mapping in our current process. We'll create a new variable to store the output address of our new remapped memory. We're going to remap a single page. We don't care where the result is placed. We're remapping from our current process rather than some other one. We want to remap the page containing our original function, the one that we're already getting a pointer to up here. We don't need anything to be copied, and we'll keep the memory protections the same as before. The end result will be, if I now run this code, we now end up with this pointer to a new page of memory at a different address than the old one. But if I print out the bytes at both areas of memory, they are the exact same. And remember, even though these are backed by the same area of RAM, from the perspective of our app, these are not just two pointers pointing to the same thing. These look like two completely different areas of memory with no relation to each other. From our app's perspective, we've essentially made a copy of our function at runtime, which sounds great. That should let us make more and more trampolines, exactly what we needed. So what's the catch? Well, let's try actually running this code. I will cast it to a function and we'll step into it, same as before. And now this looks a little different at first. You can see that the debugger no longer knows we're in our assembly file. It doesn't even know where this function starts or ends. It just says, you found some executable code somehow. Here are the instructions, I guess. But you can see we are indeed in our square root 7 function. We have one instruction to load the value 7 into a register and then another instruction to call square root. But if I continue stepping through instructions like before, as soon as we get to that square root call, this now looks very different from before. We've been dropped in the middle of a random function. The stack trace says we're in DYLD for prepare. And if I continue execution, we get a crash. So something about calling functions is broken here. And what's even worse, I'm running this on a simulator right now. But if we try running this on an actual iOS device, we won't even get that far. Because even though this is the exact same memory remapping setup covered in that iOS 4 article, it's been a few years and iOS security has improved to the point where it will stop us before we can even execute that first instruction. We didn't even make it to that broken function call. So we have two pretty big issues here. Let's look at both, starting with this permissions issue. This might feel like we've hit a dead end where this just doesn't run on modern iOS. But we have some very helpful knowledge here, which is that that old article was about an official Objective-C feature, a function called implementation with block. This is a fun feature that lets you do cool things like swizzle an implementation where your replacement is just an anonymous block. Which is cool, but isn't the important thing here. The important thing is I'm running this function on my iPhone, not a simulator, and it still works. Even though the teardown of this function from 15 years ago no longer seems to be valid, the function itself still is. This is part of the Objective-C runtime, one of the few things that Apple does actually open source. This is the first version of this implementation that Apple published. We can see the actual implementation right here. This calls out to another function, and if we keep tracing through what's called, we eventually get to the same VM remap style call that we have in our own code base. There's a couple minor differences here, mostly because parameter types have changed over time, but it's largely the same function call as the one we already have. This is just Apple's original implementation though. If I bring up the same file in a later release of the Objective-C runtime, we can actually see the code has changed a bit over the years, including some super helpful comments if we scroll up. And here's one that was added a few years ago that explains our problem. The kernel requires that we remap the entire text segment every time. Remember, a text segment is basically where all the code in a binary lives. So we can actually see this in the VM remap call. The original one is mapping a single page of data just like our code's doing. But Apple has updated their version to remap all of the code from whatever binary they're mapping. We've confirmed that we're not supposed to be just remapping small parts of code around. We can work around that. There are kind of two options here. We could just remap everything in our binary. If we want more trampolines, we just make a remapping of essentially our entire framework and there will be more trampolines somewhere in there. That feels pretty wasteful though, especially because I want to implement this in Swift, and Swift binaries can get pretty large pretty quickly. The second option is actually what Apple's doing. They split their trampolines into their own dynamic library, just full of trampolines. And that way they can remap that whole thing without being too wasteful. Fun fact while we're here, while loading those trampolines, the Objective-C runtime checks if you're the Steam app and behaves differently if so. Neat. So anyways, this should work. We should be able to mirror what Apple's doing here and ship our code in two pieces, one containing all trampolines and one containing everything else. But that's fine for Apple, but it kind of sucks if you're picturing a dependency that you pull into your app. Like either that's going to mean pulling in two frameworks or pulling in one framework that depends on another one, but then we've got like two packages to maintain on our side. Maybe one's embedded in the other, but that's a super unusual setup that will surely break things somewhere. So what I want to try is actually a secret third option that you would not know from looking at the Apple implementation. We've been talking just about remapping memory from one location to another. But as we talked about earlier in this video, you can remap many things, including files. We know that all of our code, including our trampolines, are already in a code-signed binary somewhere on this phone. That's how an app works after all. What I want to try is finding that binary file and mapping it into memory. And luckily, that's not that hard to do. First, we need to figure out what binary file actually contains our square root 7 function. We can do this using the DL address function. That'll give us the path to whatever binary contains this function, essentially our own binary in this case. And then I'm just going to open that file. Then I'm going to use that same mmap style call we saw for allocating pages of memory earlier. I'm going to say put this memory anywhere, remap one page of memory again, but this time we want the memory to be executable. We'll use map private again to say we want this to just be for our own process. And this time I'm going to pass that file descriptor in, meaning we want to remap that file into memory. Now this last parameter is actually a little bit tricky. What offset do we want to start mapping memory from? We need to say where this function is located. Literally, where are the bytes in this file that correspond to this function's instructions? If I comment this out for a second and just build our app, we can find the resulting binary ourselves, and we can open that in a disassembler to see what sort of offset I mean. So I'm just going to drag our binary in, and if we find that square root 7 function, we can see that right now it lives at hex 8000. We can confirm this with the hex editor. If I click on these instructions and open our disassembler's hex view, we can see the bytes corresponding to those two instructions. And if I open just a plain hex editor and drag our binary file in, all the way down at hex 8000, we'll see the exact same bytes there. Which confirms if we're able to remap this file into memory and we know this starting address, we will get the bytes corresponding to these two instructions. But we can't just hardcode in hex 8000 here. That number presumably isn't stable and depends on whatever else is in the binary. You can actually look up this value yourself at runtime. It's annoying, you kind of have to parse through the binary file yourself, like looking up where each segment is and what memory it corresponds to, stuff like that. But I'm gonna go with an easier option. We already said in our assembly file that our code should be aligned to a multiple of hex 4000 bytes. It makes sense in this case why we saw it at exactly hex 8000 then. But right now there's no guarantee of what multiple of 4000 it's gonna end up at. But we actually can guarantee that using a linker order file. I wanna make a new file called linker.order. The name doesn't matter a ton here. And we can use this file to specify the order that we want things to appear in the binary. We just have to update our project settings to say that that order file exists. Now we are guaranteeing that this √7 symbol is going to be the first bit of code in the binary. It's not going to be at offset 0 because there's all sorts of metadata that needs to go there first. But if we rebuild and reopen our binary in a disassembler, we can now see that our assembly code lives at hex 4000. In fact, it's the very first thing appearing in this binary. And so we now have a guarantee no matter what other code lives in this code base, that our custom assembly code can always be found starting at hex 4000. Long term, we probably still want to look this up at runtime. You can see an example of how that works in the GitHub repo link below, but for now, this works. Now, when I run this code, we can use memory read to see what bytes are actually visible at this address. And just like before, we should see the exact same bytes across our normal function and our mmap version. Remember, when we tried remapping executable code to a new area of memory on a real iOS device before, the kernel would stop us as soon as we tried to execute a single instruction. But this time, by mapping the actual binary file containing these instructions back into memory, this time, the kernel does not stop us. Even on a real device, we can execute this remapped code. So this is a valid way to remap part of our executable file into memory at a new location. This will let us make more trampolines without mapping a ton of redundant data or having to worry about multiple binaries. So that's one huge issue fixed. It still crashes when we try to call another function, but that's progress. Let's take a closer look at that crashing function call in our disassembler. We load the value 7 into the register D0, as we know already, and then we branch to the square root function. Now, the really important thing to know here is that most assembly instructions that are referencing other parts of the code base are relative to their own address. Our disassembler here is saying this is a branch to the square root function, but that's actually a simplification for our benefit. If I click this instruction and then navigate back to our hex view, here are the 4 bytes that make up that instruction. Let's look at what those actually mean. I'm gonna bring up armconverter.com again, and this time I'm gonna ask it to convert the other direction from bytes to instructions. And if I paste in these bytes, we can see they don't literally translate to something like branch to square root. They literally mean branch hex 61C0 bytes forward. This instruction lives at hex 4004. So if we take this instruction's address and we add in this branch offset, we can see this equates to branch to whatever's at this address. And if I go there in our disassembler, we can see that's the square root function. That's why we see our function crash. When this instruction was first assembled, it meant jump hex 6000 bytes forward to the square root function. But now we've taken that same instruction and dropped it somewhere else in memory. We're jumping thousands of bytes forward into the middle of a random function where we don't have any of the right context set up, and we eventually crash accordingly. If we take the bytes that correspond to instructions like this and drop them in some other random part of memory, they're now going to be pointing to the wrong locations. And this is a tricky problem to solve. We need our assembly code to call our shared Swift handler, but we need our code to do that in a way that works regardless of where it's loaded in memory. There's not really a good way to completely avoid these relative types of instructions, and we can't change where they're pointing on the fly since we're remapping the same literal bytes over and over. But here's the big question. If these functions have to be pointing somewhere, can we make sure that whatever memory they're pointing to actually happens to be useful? Let's code up a very literal representation of this problem. I'm gonna have an assembly function that adds hex 4000 one page of memory to its current address. It's then gonna read whatever value is at that address and return it. This instruction is using a relative address. If we just copy this code around, it's gonna be pointing to garbage. But how could we set this up so that this function still returns an actual useful value anyways? Well, for that, we'd have to control whatever memory this is pointing to. If this function lives at hex 14,000, then we also need to control the memory at hex 18,000, where this instruction is gonna be reading from. And we can maybe do that. Remember, all of the memory remapping functions we've looked at today have a parameter where you can request a specific address for the resulting memory to live. So we can update this code to make a remapping of our new function. But this time, after we've remapped, I'm gonna take the address of our remapped function, wherever iOS puts it, doesn't matter. And I'm gonna allocate a new page of data at hex 4000 bytes from our function, one page over. And this time it's gonna be writable memory, not executable. And we'll go back to using map anonymous to say we're not remapping a file here. We just want a block of memory. Now we should be remapping our assembly function to memory and then creating a new page of data directly after that. I'm gonna go ahead and add an assertion that that relationship is true, that our data pointer lives hex 4000 bytes after our function pointer. And now we can write an integer value to that data page by saying that data page is actually a pointer to an int and then updating that int. And then just like before, we're casting the pointer to our function memory back to a function, and then we're calling that function. So let's make sure everything was set up correctly. We have our function pointer, which again, iOS assigned to some random address. And then we have our data pointer, a page of data that we requested be placed hex 4000 bytes after the function pointer. And you can see that worked perfectly. And if I were to read from that data pointer, saying we want one value of type decimal, we should see this number 12 that we're writing right up here, and indeed we do. And finally, if I continue execution, we can see that this new function we made, which is built to just read a value one page over from itself, successfully got this 12 that we wrote there and returned it. This is how we can write code that works no matter where it's loaded, not individual pages of memory, but pairs. One page of executable code and one page of data. Any data that our code needs, we write to the neighboring page and it loads from there. Of course, in reality, iOS is gonna be fighting us a bit here. If I rerun this a few times, we'll see this assertion getting triggered quite frequently. Not only are things in the system being constantly allocated and deallocated, meaning someone else might have gotten the neighboring page before we could get to it. There's no guarantee that neighboring page was even free in the first place. The system might have had one page of memory free in some fragmented area and remapped our function there. There's some unpredictability here. We can tip the scales back in our favor though. We know we need an area where there are 2 consecutive pages of memory available. How can we find that? We just ask for 2 pages of memory. This will return an area that we know has enough room for 2 pages of memory in it. So let's start by requesting those 2 pages at wherever iOS wants to give them to us. And then we'll ask for our function pointer to be created in the second half of that memory. There's actually a flag we can add to our call, mapFix, which basically means this address parameter is not a suggestion. Give me that address, overwrite what's there if necessary. This would obviously be unsafe if we didn't know what memory was there. But in our case, we know it's the second page of data we allocated just above. There's nothing important being overridden there. Now, because we changed the order of these, we'll have to update our code and update our assembly to say read from the page before us this time. And now if we run again, no assertions, this code works perfectly every time. And again, our goal is to use this to write trampoline code that can work no matter where it's loaded in memory. So let's look back at our original trampoline setup. First, let's update this to start on a page boundary as well. That makes the remapping a lot easier. And then let's go back to just creating a few trampolines for now. So now that we figured out how to remap executable code into different areas of memory, what would happen if we tried doing that with our trampoline setup? Let's try it and find out. I'm gonna add a new method to our trampoline setup class called allocate trampolines. And let's paste our current remapping code in there. So the first thing we need is a file descriptor for whatever binary file holds our trampolines on disk. Basically the same setup we're already doing here, but I'm gonna move it to our class's initializer and to some of these constants up above. Again, just making sure we're doing this work once. And then just like before, we're gonna allocate 2 pages of writable memory and then overwrite the second page by remapping our trampolines file in. So we end up with one page where we can store data and one page that contains our trampoline handler followed by trampolines. The goal for this method is to essentially return a set number of trampolines we can use. So returning something like an array of trampoline seems like it would be helpful. And for now, maybe a trampoline just contains a pointer to wherever that trampoline is implemented in memory. And now if we have, say, 100 trampolines, we can iterate through all 100, compute where that trampoline's implementation would live, which is gonna be somewhere within this executable block of memory. Let's actually rename that. So each trampoline is gonna be within that memory plus some fixed offset. Remember, the first trampoline is actually gonna be a few bytes down because it comes after that shared handler. But we can do some math to figure out what that offset would be. Now this will give us the address of our first trampoline, but we need to add on one more offset that takes into account our trampoline index. So we add 0 bytes to get to the first trampoline, 8 bytes to get to the next one, 16, so on. And I'm gonna actually move these constants over to our trampolines file. That feels like a better home for them currently. Now, of course, we're hard coding 100 trampolines here, which matches what we're doing in assembly. But we're mapping a whole page of memory every time, so it would be a lot nicer to just say, fill the rest of the page with these trampolines. We can actually do that. We just need to calculate in advance how many trampolines that would be. We know the size of a page is hex 4000 bytes, and that each trampoline is 8 bytes long. So if this page was just full of 8-byte trampolines, we could just divide these two numbers and know exactly how many would fit. But we're also remapping this handler. In order to know how many trampolines can fit on the page, we need to know how many bytes this handler is taking up. Luckily, that's also pretty easy. After that function is done, we can use a period to say get the current instruction address, just like we're already doing in the trampolines down here. And we can take that address minus the starting address of the trampoline handler to figure out exactly how many bytes were used by all these instructions. Then we can figure out exactly how many bytes are remaining in the page and divide that up to figure out how many trampolines can fit in the remaining space. And now that's perfect. We are cramming exactly as many trampolines into this area as we can. But we still need a way to know exactly how many trampolines this is from our code. And we could expose this in a way that Swift could read, but maybe slightly easier is I'm gonna add one more label after all our trampolines are done to mark the end of the trampolines, which is probably a thing we want anyways. And then I'm gonna load that address from within Swift as well. And we can use that to derive the total number of bytes used by our trampolines in any given remapped page. And from there, it's also easy to get the number of trampolines in that page. So now we can iterate over the exact correct number of trampolines. And finally, we can take all these pointers to all these different trampoline implementations and use that to return this higher level trampoline value. So now when this allocate trampolines function is called, we're gonna reserve 2 pages of memory. We're gonna overwrite the second page with a remapped copy of all this assembly code. And then using that remapped page, we'll return a bunch of trampoline values, each one pointing to a brand new ready to use trampoline. Now I'm gonna get rid of some of our old trampoline management code. And I'm gonna create a new property that contains all of our currently available trampolines. And when it's time to actually swizzle a method, I'm gonna get an available trampoline. And then we'll use that trampoline's implementation as the replacement for whatever method we're swizzling. And of course, if we're out of trampolines with this setup, we can just make more. If trampolines is empty, just allocate some more trampolines. Now that's all the setup we need to remap trampolines and use the remap versions, but we still haven't answered our earlier question, which is what breaks when we do that? So let's actually test. I'm gonna switch back to just swizzling our example code where we swizzle messages and messages v2, which is gonna make it really easy to call this setup method and then step through exactly what's happening. Oh, and we have a typo right here. Okay, that's easy to fix at least. Cool, so just like before, I'm gonna use SI to step at an instruction level through what's happening here. And the first thing we'll see is that this is gonna internally call obfusc message send, whose job is to figure out where this function implementation lives. So I'm gonna step through this infrastructure. If you're curious right now, it's looking up if it's seen this method before and if it's cached. And now it says it doesn't have this version cached, so it's gonna look up where this implementation lives. I'm gonna skip over this call that's responsible for actually looking up that implementation. You can actually see, funnily enough, this obfusc message send internals is doing the same thing that the main thread checker is doing. Backing up all the registers because it doesn't want to mess with them, doing some implementation, and then restoring all the registers for the original function call. So, if you were curious how rare the strategy might be, that will give some answer. But perfect, this is now looked up where the implementation lives and we're branching to it right now. So if we step forward, we can see that we've ended up in one of our trampolines. So the swizzling worked, obfusc message send looked up the implementation and got one of our trampolines as a result. So as we know, the first instruction is setting the trampoline's own address into x16. And then we're gonna step to continue into our shared handler. And just like before, LLDB has no idea what code this is. It doesn't know the bounds of this function. It just says you found executable code somehow, yippee. But we can recognize this as our shared handler. We have a bit of function prologue and then we are storing all these registers down below. So even though we remapped all this code elsewhere, the jump from trampoline to the shared handler still worked. And that makes sense. This branch instruction in every trampoline ends up assembling to something like branch 200 bytes up or 208 bytes up, 216 bytes up based on which trampoline exactly we hit. Because we're remapping the trampolines and the handler together, those instructions will always still point to the place they expect. They're a branch within a single page, within the bounds of what we're remapping. But remember, this assembly handler, after it has stored all these registers, is going to branch to a different function. That's going to translate to something like jump 100,000 bytes forward or 1,000,000 bytes back. This is a branch to something outside of what we're remapping. And if we go back to our execution and keep stepping forward, we can see that LLDB hasn't labeled that branch call at all. It doesn't think that code corresponds to any method. I bet if we actually branch to it, yeah, it's just garbage data and we should be about to crash. So in order for our remapping strategy to work, we need a way to make this call in a way that will always bring us to the correct function no matter where all of this code is loaded in memory. Remember, with our remapping setup, we have a page of writable data where we can pass additional info to all this code. So I'm gonna look up another address, this time to our Swift trampoline handler, the one we built all the way back here that is doing things like looking up a trampoline's index and calling the callback that contains the main thread check. So we've got a pointer to that now. I'm gonna take our executable page and I'm gonna get a pointer to 8 bytes just before the start of that page. That's gonna be the very end of our data page. And I'll tell the compiler to treat that as a pointer to an unsigned 64-bit value, perfect for storing a pointer. And then I'm going to write the address of our Swift trampoline handler to that area of memory. Now, whenever we remap a page of trampolines, just before that page, there will be a spot where they can look up where that shared Swift trampoline handler lives. Over in assembly, I'm gonna take whatever's in register X16. Remember, that's the address of the trampoline we just came from. And I'm gonna use a bit clear instruction to say clear off all bits below our page size. This is effectively saying round down to the nearest multiple of page size, or in other words, get the starting address of our page. And now I'm gonna read the 64-bit value from 8 bytes before that address. The very end of our data page, that's where we wrote the handler's address from our Swift code. And then I'm gonna branch to whatever that address is. Now let's try stepping through this again. I'm gonna go through all the same obfusc message send infrastructure as before. So now we're entering our trampoline, we are branching to the assembly handler, we're backing up all our registers just like before. And right now, register X16 still contains the address of whatever trampoline we came from. But now this instruction should round that down to the nearest page size, which we can see that it did. And now we're gonna take that address and read the value 8 bytes before it. And looks like we got an address out that should be where our Swift handler lives. And now we're gonna branch to that address. And when I step forward one more time, we can see in spite of coming from a random area of remapped memory, we have successfully made it to our Swift handler. This is how the page pair setup is able to overcome a lot of limitations we would expect from relative addresses. It's not actually too dissimilar to how dynamic linking works in general when making calls across frameworks. Just like we saw with square root earlier, or if we step into this DL open call. This little function is loading some value into X16 from some data page elsewhere in memory, and then branching to whatever's in that register. And when your app starts up, the dynamic linker is responsible for going to all these data locations and setting them to the correct values. Just like our trampoline handler was responsible for setting the right value so our assembly could find it later. Cool, so back in our Swift handler, we're almost through, but we have one more small issue, which is, remember, this handler is gonna look up the address of the first trampoline and then compare with the address of the trampoline we're coming from and use that to compute the index of that trampoline. Problem is, this is now a nonsense comparison. We're taking the value of our first unmapped trampoline, like in our original page of data, and we're subtracting from that the address of the trampoline we just went through somewhere in a completely random part of memory. These two addresses are not related to each other anymore. And we can see that if we keep stepping through, like our trampoline index ends up being 1.7 million. And we're gonna try to look up that index in the shared array and of course, crash accordingly. And we could patch up this index calculation, maybe look at the trampoline's offset within the page we're coming from, or store the addresses of all the trampolines we've used and look up the index in that storage. But here's the thing, the whole reason for this index is to look up the trampoline data in this giant shared array. But we have a better way of storing data now. We're already allocating a whole page of writable memory right next to these trampolines. So instead of having this giant shared array with all the weird indexing and maybe weird threading considerations that come along with that, let's instead say every trampoline gets to store its own data in the data pages that we're already creating. Now, because each trampoline is 8 bytes long and we have a one-to-one mapping between executable memory and data memory, we have one page of each, then each trampoline's data can also only be 8 bytes long. We could work with that. That's enough bytes to store a pointer to somewhere else in memory where the trampoline's data really lives. But then we have to deal with keeping that other memory alive, and it's also a bit less performant given we're routing basically every method call through this. We can do a bit better here. Right now we're only allocating one page of data, but that's up to us. We could say allocate 10 pages of data for every one page of executable memory. We just start by allocating enough room for data and code, and then we remap everything after our data pages with executable code. 10 pages of data, 1 page of code. But how much data do we actually need? We know we want to store one trampoline data value for each trampoline. That's going to require a certain number of bytes. These are 3 8-byte pointers, so it should total 24 bytes. But let's not take my word for it. Instead, we can use Swift's memory layout functionality to make a constant that represents how many bytes this struct takes up when placed in continuous memory like an array. So if we want to know for one page of trampolines how many bytes we need to store data, we can compute that. And if we want to compute how many pages of memory that corresponds to, we can compute that too. And now we can say based on that math, just allocate exactly however many pages we need. Now, when we're creating these trampoline values, just like how we're calculating where each trampoline's implementation lives, we get the address of the first trampoline and then add 0 bytes, 8 bytes, 16 bytes, so on. We'll do the exact same thing to divvy up our data pages. We take the pointer to the start of our data, and then we add 0 bytes for the first trampoline, 24 bytes for the next one, and so on. Where that stride is computed at compile time based on exactly how much data is needed for each trampoline. Now, I'm gonna say that that's a pointer to some trampoline data, and we can pass that pointer along to our trampoline initializer. Now, each trampoline has a dedicated place where they can store their data. So let's update the code where we actually set that data. So instead of writing this to a giant shared array, I'm just gonna say write that same data to wherever the trampoline's data pointer is pointing. Better yet, we don't even have to expose this pointer. In our trampoline struct, we can make a new computed property that just automatically reads or writes whatever is in that pointer. And we can make the fact that this data is backed by a pointer to some weird area of memory just completely an implementation detail. And now this code becomes as nice as just setting trampoline.data. And of course, we actually have to read that data now too, but that should be pretty easy. Instead of looking up the address of that first non-remap trampoline, I'm instead gonna take the address of whatever trampoline we came through and clear off the lower bits again to round it down to the nearest page size. That'll get us the starting address of whatever page contains these remap trampolines. Next, I'm gonna take our trampoline's address again and subtract away the start of the page to get the trampoline's offset within that page, and then subtract away that constant we had earlier that was basically the number of bytes in the handler. Meaning the first trampoline within this page will have an offset of 0, then 8, then 16, then so on. Same as before, we'll divide by trampoline size to convert that to an index. Then we need to get a pointer to where the pages of data that we allocated start. And we can do that by taking a pointer to our executable page, and then use the constant we already made that represents how many bytes of data we're storing for a whole page of trampolines. Right, like if we were storing 3,000 bytes of data, if that was how many bytes all of our data pages were, we take our executable page address, we subtract 3,000 bytes, and that gets us to the start of those data pages. And from there, we can get our actual trampoline data by taking that data pointer, the start of our data pages, taking the size of one trampoline's data and multiplying that by our trampoline index. That's gonna be the address where our trampoline's data lives. Oh no, is Xcode crashing? We made it pretty far into recording without an Xcode crash. All right. We're gonna tell Swift that that's a pointer to trampoline data, and then we're gonna read whatever data is at that pointer. And finally, we can get rid of this old shared data array. This time, just looking up the data in the pages we allocated next to our remap trampolines. And if we rerun finally, look, I know this looks the same as it did 40 minutes ago. But this is so cool. For this to work, we are remapping our own binary file into memory, creating a new copy of these instructions somewhere else, which we can do as many times as we want. We are creating more code on a platform that really doesn't allow that. And the end result is that if we go back to swizzling all of UIKit here, just like we were doing before, even though this is a super small binary containing only a single page of trampolines, it's able to essentially self-replicate to handle literally whatever we can throw at it. So there's really only one question left, which is what can we throw at it? Right now we're swizzling all of UIKit, but we can maybe just swizzle everything. We might be setting the coveted world record for most swizzles here, but let's see if we can actually pull it off. It wouldn't be too hard to swizzle more things than just UIKit. Instead of looking up one specific image, we'll move this logic down to a new method that swizzles any image we pass to it, and then we'll just call that on all the images. Now, if we're swizzling more foundational stuff, it would be nice to do that as early in app launch as possible. As far as I know, there's no nice way to do that from Swift, but I can mark this method and class as @Objective-C, and make a new Objective-C class to call that method as soon as our image is loaded. Great, so we're gonna be swizzling a lot, so I'm gonna add a new property to keep track of how many we've set up, and maybe log every 100 swizzles. Let's see how that works. Okay, that's working, but it's doing a lot of work. It's not very great for our app launch time. This brings up one detail about Apple's implementation that I didn't cover. Remember when I said, and my favorite part of all this, there's no special API that Apple is using here that only they have access to. That's only partially true. It's Apple, they're gonna cheat a little. Even when we were just swizzling UIKit, it still took a second or two for the app to start up. Apple wouldn't ship a dev tool on by default that adds that kind of delay, so how are they avoiding it? Well, the slow thing we're doing here is actually this method set implementation call. This acquires a lock that is shared across the whole Objective-C runtime. You could imagine some downsides of multiple threads messing with these implementations otherwise. And then it performs more work like clearing the method cache afterwards. This is a semi-expensive call. So what does Apple do? Well, if we bring up the disassembly of the main thread checker again, when we go through all the methods and we call this prepare swizzle on each one, once all that's done, we call a function called class replace methods bulk. If you haven't heard of it, it's because it's a private function. If you Google it, the only references to it you'll find are from some random loon on the internet. This function swizzles a bunch of methods at once so that expensive work like acquiring the runtime lock only has to happen once per class. Best to not ship this in a public app unless you know what you're doing, but we can use this function pretty easily. I'm gonna look it up at runtime just like all these other functions, and then I'm gonna define a type alias that matches the signature of that function. It takes in a class to swizzle and then a bunch of C-style parallel arrays of selectors, the new implementations, the method types, and an account for those arrays. Now, when we're swizzling a class, we'll get a reference to that function and cast it to that type alias. And then instead of having this function do the actual swizzling, we'll have it return some data about what it wants to swizzle. So I'm gonna define that up here as well, where we'll pass in a selector and an implementation and a method type. And now we'll update this method to say it returns that value and actually set up the return down here. And that's easy. We already have the selector pretty easily and our trampoline implementation. we actually haven't had to deal with method type information during all of this, because that's the beauty of the setup. It doesn't matter. But this function requires it, so we'll grab the method type information to return that as well. Then when we swizzle a class, we'll just collect all those replacements and then pass them along to class replace methods bulk. All right, let's see how that fares. Oh, it's still slow, but it's because we're also relieving in our original swizzling. Let's get rid of that. Try one more time. Wow, that was 800,000 methods like it was nothing. That was a second or two. We crashed, so we're not done yet, but that was really impressive. Okay, so we've hit an exception. Could not find executable name for frontboard services. That's hopefully not due to any bugs in our implementation, but even bug-free, we're changing how some methods are defined. That could break some assumptions in some low-level code. So let's look at what's happening. We're crashing an FB settings set counterpart class, and specifically in a block that it's calling. Let's look at that in the disassembler. And we can see that this function is looking up the FB settings class, and then it's calling get method implementation. It's looking up the address where one of its methods lives, and then it's looking up the binary image containing that address. Okay, so it makes sense why we're hitting this error. Some bit of code is looking up a method on this class and checking what image it lives in. It's expecting to find an Apple System Framework frontboard services, but we've replaced all the methods in that class with our own, and so it's getting our binary instead. So that's an easy fix. Let's just not swizzle that class. I'm also going to comment out our line of code that is printing every method being called that is getting unhelpful as we swizzle more and more things. We're going to say don't swizzle anything related to FBS settings. Okay, so now if we rerun, wow, without that log too, we absolutely breezed through 800,000 methods. That's incredible. Okay, similar issue. Somebody's complaining about method signature for selector. This is a function used to do some runtime trickery that we probably don't want to mess with either. So I'm just going to go ahead and exclude that too. Hopefully we don't have a ton more of those. Oh, did it work? I think we're in. We didn't crash. Oh God, I think we swizzled everything. Let's add some logging back to our swizzle callback. I'm not going to log everything. That would probably break my computer. But we could maybe log every 1,000 calls or so. Okay, let's try that. Okay, app is launching. Whoa, we got 800,000 calls during app launch. This is an empty app, but that's still maybe higher than I would have expected. What if I rotate my phone? Whoa. Okay, rotating an iPhone calls about 100,000 methods in an app. That's a bit of trivia that neither of us knew we were gonna learn today. So one last thing, this is swizzling all 850-ish thousand methods that are available from kind of the default frameworks that an empty iOS project would pull in. But we could pull in more. I'm gonna use the IPSW tool, and I'm gonna say in this DYLD shared cache file that holds basically all the frameworks that your phone uses, give me all the dynamic library information within. And let me paste this into Sublime. So we've got 4,000-ish different libraries, frameworks that are present in that cache. So what I'm gonna do is clean up this list a little bit. I'm just gonna cut out everything before the framework name and wrap them in quotes. I'm gonna make a new function whose job is to try to load everything in that list. Just pasting them all in for now, why not? And for framework, in all frameworks, we'll log it and attempt to open. And then as part of our setup before loading anything else, we'll call load all frameworks. This is gonna take a bit. I think that's gonna take like a few minutes. Okay, so there we go. After literally, I think a 5-minute app launch, we are at 1 million methods swizzled. 1.5, 2.7 million methods swizzled. Thus, I think conclusively taking the world record for most methods swizzled. Thank you so much for watching this feature-length documentary on how a random developer tool works. The code's on GitHub if you want to take a look. Thank you again, Landon Fuller, for the incredible blog post 15 years ago that really powered the second half of this video. This has been such a crazy fun one to make, and there are more videos on the way that I am even more excited about. These things are often entire research projects and take a ton of time to make, so thank you for all the incredible support in the meantime. It really means the world. Thanks again. I will catch you for the next one.